Hey everybody, Dr. Retzik here with you. This is our fourth video in section 7c. Today we aim to characterize isometries. Let's get started. So the setup is we got a finite dimensional inner product space V. Remember, an isometry is an operator S with the lovely property that if you feed S an input V, which produces an output SV, the norms are the same. So an isometry neither shrinks nor stretches any input. Just as we had a big theorem characterizing positive operators, we have a big theorem in 7c characterizing isometries. I think it's theorem 7.42, and here's what it says. So this is theorem 7.42, I think, in the book. Hypotheses are simple. Let S be an operator on V. No restrictions here on what the underlying scalar field is. You just have some operator on a finite dimensional inner product space V. The following are equivalent. And then there's this long list. Okay, so thing A, S is an isometry. Okay, so everything that follows is equivalent to S being an isometry. B. If you take the inner product of SU with SV, it comes out the same as the inner product of U with V, and that's true for all vectors in the space. So people like to say isometries preserve inner products. The inner product of two things on the left, U and V, comes out the same as the inner product of their outputs, SU and SV. Okay, delightful. Thing C. If E1 through En are orthonormal, then SE1 through SEN are orthonormal too. So people like to say isometries preserve orthonormality. All right, thing D. There exists an ON basis, E1 through En, such that SE1 through SEN is orthonormal. Well, that follows pretty easily from C. Certainly there exists an orthonormal basis by Graham-Schmidt, and then by part C, if we do S to that basis, then we get N orthonormal things. Orthonormal sets are linearly independent, and therefore those N orthonormal things on the right side of the picture, SE1 through SEN, are a basis as well, for that matter. Okay. Thing E. S star S is just the identity. That's remarkable. Thing F SS star is just the identity. Thing G, S star is an isometry. So that's nice. S is an isometry if and only if S star is an isometry, if we believe in this theorem. And then finally, thing H, well, you can guess it from these two things. And this comes all the way back to something that we were talking about in class when we first broached the subject of adjoints. We were wondering, wait, is S star ever the same as S inverse, right? Like S kind of goes left to right, S star goes back right to left. It kind of looks like the picture for inverses. And we said, no, not usually. There's no reason to believe that. Well, here we finally get the complete answer. S inverse is S star is equivalent to S being an isometry. So if you wanted to know, hey, when is S star, when is the adjoint genuinely the straight up inverse of S? It's when S is an isometry. Okay, giant theorem. We have all sorts of things equivalent to S being an isometry. I forgot all my semicolons. We want to prove the theorem. So the route to proving the theorem is going to be sort of our classic A implies B implies C implies D implies E implies F implies G implies H implies back to A. And so then all of those things will imply each other. This is going to be a two-part discussion. Our goal today is to get up through A implies D, and then we'll do D implies E implies F implies G implies H implies A next time. Okay, so here we go. Let's prove this. This is a very, very powerful and useful result for us. Okay, so here we go. Here's the proof. Let's do A implies B first. So suppose S is an isometry. That means it preserves norms. We would like to show it preserves inner products. And now you get payoff for an old Math 406 homework problem. Might have been weekly homework 1. In fact, it was 2 problems. So I want to draw your attention back to 6.A.19/20. You did both of those problems for homework. And let's just remind ourselves what 19 said. 19 said that in an inner product space, if you want to know the inner product of U and V, that's equal to norm U plus V squared minus norm U minus V squared all over 4. So this was an important little statement for us. Its proof back there in chapter 6, this was not earth-shattering at all. All you guys did was start with the right-hand side and actually sort of square out those norms in that numerator, and a bunch of stuff canceled, and when the dust settled, you just had inner product U comma V. Okay, and at the time we were like, oh yeah, practicing properties of norms and inner products, and it didn't mean anything to us. Right now it means something. What it means is you can compute inner products solely by computing norms. Thus, if you have a thing that preserves norms, it should preserve inner products. Okay, so let's write this out, just for the real case. Okay. Thus, if you were interested in SU inner product SV, well, you could write that as norm SU plus SV squared, take away norm SU minus SV squared, all over 4. Okay, but look what you have in that numerator. That first term is norm of S acting on U plus V squared, take away norm of S acting on U minus V squared, all over 4. But by supposition in this part, A implies B. Part A is that S is an isometry. So that means in the numerator we really have norm U plus V squared, take away norm U minus V squared, all over 4. Remember, by supposition, S preserves norms. And then by 6a number 19 again, this is nothing other than U inner product V. So, if S is an isometry, then that means S preserves inner products. Fantastic. Okay, so we're done with A implies B. Let's move on to B implies A. Okay, B implies A. Suppose that S preserves inner products for vectors in big V. Okay. Well, check this out then. We're trying to prove an if-then. We're trying to prove that if E1 through En are orthonormal, then SE1 through SEn are orthonormal. So let's assume E1 through En are orthonormal. Okay, well then, if you're interested in the inner product between Sej and Sek, well, we're under the supposition right now that S preserves inner products, so that's the same as inner product Ej with Ek. So that's 1 when J and K match, and 0 otherwise, because we're assuming E1 through En really are orthonormal. So SE1 through SEn are orthonormal too. Sorry. Okay. So once you know that an operator preserves inner products, then it has to preserve orthonormality. Oh, why did I write B implies A up there? This is B implies C. B implies C. Okay, let's go for C implies D next. C implies D. Okay, well in this one, we're supposing C holds and trying to argue that D holds, so let's just write it like this. Suppose S preserves orthonormality. In other words, if E1 through En are orthonormal, then S of E1 through S of En will be orthonormal also. Okay, and what we're trying to argue is that there exists an orthonormal basis such that when you do S to it, the result is still orthonormal. Since there exists an ON basis, E1 through En, and we are assuming part C, SE1 through SEN is also orthonormal. So there's not much to C implies D. C is the much bigger statement. Once you know orthonormality is preserved, certainly by Gram-Schmidt there is an orthonormal basis. And if S preserves it, then SE1 through SEN are orthonormal. And for that matter, they're a basis because there's n of them and they're linearly independent. And maybe there's even more tacitly being said here in part D. Okay. The next section of the proof is that D implies E. And I want to set it up. Okay, so we are supposing in this section of the proof, E1 through En is an orthonormal basis for V. Okay. Now, from that alone, we're trying to argue that S star S is the identity. All right, so we have to show that S star S acting on any vector whatsoever just leaves that vector fixed. The first step in this direction is to see how S star S interacts with these basis vectors, and then from there, try to extend that understanding to how S star S acts on any vector. So first observe that if you look at the inner product of S star S Ej with Ek, where the E's come from this supposed orthonormal basis, E1 through En. Okay. By definition of adjoint, that's Sej Sek. Now, we are assuming part D and we know that Sej Sek is orthonormal by part D. So that quantity, inner product Sej Sek, is either 1 when j equals k or else 0. Which is the same as this inner product, Ej with Ek. Again, 1 when j equals k, 0 otherwise. So at this moment, we have established that S star S interacts with our orthonormal basis vectors in this way. S star S acting on Ej, inner product with Ek, is the same as just Ej, inner product with Ek. This is the first step in part E, or in part D implies E. We want to extend that now to an understanding of how S star S acts on any arbitrary vector in the space. And I have to say, I think your book is somewhat flippant about it at this moment. At this moment, your book says what people like to say. Oh, and says, since that's how the operator acts on the basis, that's how it acts on any vectors. Yeah, okay, I like that as sort of an operator theoretic principle. Once you understand an operator on the basis, then by way of linear combinations, you understand that operator on any vector. I mean, I'm with it in spirit, but I think there's a little bit to be said at this point about how we bootstrap from the current statement concerning S star S acting on the E's to the broader statement concerning how S star S acts on arbitrary vectors. So we're going to pick up right from this line tomorrow, and we're going to see how to make that bootstrapping argument. All right, but that's good progress. Halfway through our big characterization theorem for isometries. All right, see you next time. Bye.